Okay. That's not right. Okay. So let's talk about, so we just dealt with this homogeneous case, and now I'm going to, just for the sake of your notes, talk about the non-homogeneous case. Okay? Again, I'll explain what those terms mean later when I feel we have reason to use those obscenely cumbersome terms. Okay? Alright, so let's go. Alright, so I do know about population examples. I could keep using population examples, but let's do something close to all of our hearts, student debt. Okay? So, let's imagine that the following situation, okay? You, after 4 years of completely useful learning, devoted entirely to your subject and to nothing else, you have racked up $80,000 in debt. Right? That's $20,000 a year. That's what usually tuition looks like. Okay? That is where your debt starts. Okay, I'll call this D at 0. Okay? And let's say that you went to a real shyster on this one, a Shylock, when you took out this student loan. And you got a loan with the APR, or of 10%. Okay? So the idea is that you're paying back 10% of your debt, as every year you have to pay back 10% of your debt as interest. Okay? As in, just to keep your head above water, just to keep it from not growing, you have to pay back 10% of this. Okay? Alright, so how do we and the idea is we very much like to know when we no longer have to pay that anymore. Alright? And let's just say that, given whatever job you happen to have, that you're able to pay back something like, you have an income of $10,000 of, not quite income, but this is basically what you're paying off per year. That's what your income allows you to do, is pay off $10,000 each year. Okay? And you would very much like to know whether that's a sufficient amount of money so that you can pay off your loan, maybe before you're dead. Okay? So let's see if this is a reasonable amount to pay off, or maybe we have to pay more, or maybe we can pay less if it's really quick. Okay? So how do we represent this? Okay? How do I represent this? Well, I'll represent the following way. Okay? We all know that, okay, what's the rate at which my debt is changing? Alright? What's my rate at which my debt is changing? Well, I know that this is the APR right here. That basically I'm paying 10% off it per year. So let's just say that, okay, it's going to be 1/10 of the value of my debt. Right? So if I didn't do anything to this, and I went another year, then I have to pay back a whole extra 1/10 of my debt right there. All right. So, all right. But the thing is, I'm not just letting the debt grow and grow. I'm not the U.S. government after all. I'm trying to pay this off eventually. So I'm going to have to put this in there somewhere. So what I'm going to do is I'm just going to subtract it from there. This $10,000. Okay. Now, one thing that we see here is that just this problem right here, without that 10,000, that's something we're already familiar with, right? We already know how to solve that. That's a regular exponential function. But with this 10,000 that I'm trying to pay off, that I'm trying to decrease my debt by each year, this gets a lot more complicated suddenly, right? It will, as you will see. So, okay, what do I do with this? Where do I go with this? Well, one thing is I could just sort of grope around and throw out different solutions as I felt like it, and just see maybe I can modify this or do that. And that's one valid way, like I was doing earlier. But for this time, I think I'll maybe try to work smarter, not harder, and let's just try to manipulate this a bit and see where this goes. So let's just put the D's together, okay? Let's just put the D's together. Let's see what happens. So I get minus 1/10 d of t equals negative 10,000. And you know what the hell? I feel like writing this as plus negative 1/10, like that, because sometimes addition is better, okay? Now one thing that's really gross about this problem, the thing that's like making this really painful for me, is the fact that I have a d here, and I have a d there, and they're kind of separate from each other, right? As in I put like some function like sine here, I get some other weird thing like cosine over there. I put in like a e of 2t over here, I get a 2e2t over here. Like it would be, you know, it's in a sense it's not easy to handle right here. It's sort of like imagine if you had to solve x squared plus 2x plus equals 5. Imagine you had to solve that problem and you didn't have the quadratic formula and you didn't have the factoring. Okay, you're just trying to solve this by just sort of plugging in numbers, and it's sort of like, oh, okay, so let's try 2. Well, I get 2 over there, and then 2 here, and then 2 squared over here. Does that equal 5? No, it doesn't. It would be very awkward. Somehow you sort of want to do like the quadratic formula does, and give you a nice way of saying, oh, x. Well, that's just going to be plus or minus. That's going to be minus b plus or minus the square root of all that other stuff that we learned about. Minus 4ac over 2a. We like to, since somehow, instead of having 2 x's here, we like to just have 1. And same thing over here. Instead of having 2 d's over here, 2 separate d's, it'd be nice if we just could have 1. All right, so that's kind of an idea there. Does that make sense, guys?
Yeah.
Of like, okay, this is a mess because there's 2 of them. Just like it's a mess over here because there's 2 of them. Can we do something more like that over there? Okay, well I'm thinking, how can I handle this? And I look closer at this, I think, I have a derivative here, and the original over there. Does that remind me of anything? Product rule. Kind of reminds me of the product rule, just a tiny bit, I have f of g, I take the derivative on this guy. And what happens is, okay, I get the derivative f times g plus f times g derivative, okay? And I see that here, so I have the derivative and the original. Derivative, original. Now, one thing though is that that works with the f part of this, but I don't see any parallel with this g right here. I don't see any parallel at all. It's like, okay, I have negative 1/10 over here, and the only other coefficient I have here is 1, in a sense. This is multiplied by 1. That's all I can do. And 1 is clearly not the antiderivative of negative 1/10. Okay? So that does not work. Okay? Like this will not work in its present form here. So I think, okay, is there anything I can do to this problem that will give me something else? Something else that will look kind of more similar. Or maybe where I can somehow use this rule. Okay? I think, oh, what the hell? Let me just multiply everything by some function, okay? And that some function I'm going to multiply everything by, I'm going to call mu of t, okay? And how you pronounce that is mu, all right? Mu of t. It looks like a u except like a longer tail on the front, okay? What's the tail you have in the front? Okay, so we have mu of t. So I multiply everything by that, okay? So I have, and by the way, this guy right here, we're going to call him the integrating factor, okay? And the reason why is because, well, he's just some factor that helps us integrate. Okay? So let's see what happens if I multiply all this by mu of t. Does that give me any ideas? Okay. Does this give me any ideas? Well, let's see. Well, earlier I was looking at this guy here, and I was thinking, I have a derivative here, and the original there. It'd be nice if I had a derivative there and the original here, but I don't have that. But hey, let's look now. Derivative here, original there. What if this were the derivative and this were the original? Then I could actually use maybe this product rule right here, and then in some way be able to take basically these f's and just put them all together like that. So instead of having two of them, I just have one of them, like this. Okay? So I'd really like to make it so that, oh, this guy, as in just like how this is the derivative of that, I would like this to be the derivative of that. So what am I asking here? I'm asking the following. I want the derivative of mu of t to equal negative 1/10 mu of t. I know how to solve that. I know how to solve that. The solution, or one of them, is just e negative t over 10. E negative t over 10. So I see here, hey, if I just multiply this whole thing by e negative t over 10, I can do this. Alright, and I can basically make it so, okay, these two derivatives here, these just turn into the one thing right here. Okay? And we're going to see why it's really valuable in a second. Okay? So let's do that. Let's do that. Let's rewrite the equation with that. E negative t over 10 d of t, d derivative of t, plus negative 1 over 10 e negative t over 10 is, and then d of t. This is equal to negative 10,000 times e negative t over 10. And we just want to remember that, again, the integrating factor I defined here was e negative t over 10. Okay, so I have that right there. What do I do with it? Well, I can do now that the chain rule, the product rule, except in reverse. Okay? I recognize, hey, this right here is just equal to e negative t over 10 times d of t. Derivative. Right? I take the derivative of this guy, I get this product rule right here, and that's what this equals over there. And suddenly, instead of having two of these bastards to deal with, I just have one. I just have one. One straight d. Okay? That's great. That's great. It's just like over here, if I basically took, oh, I have two x's over here. Well, hey, now I just have one. Now I just have one. I can solve this guy. Okay? And now what do I do? Well, what I do now is I can basically just take the integral on both sides of this. Okay? So I'll rewrite it. E negative t over 10 d of t dt equals the integral of negative 10,000 e negative t over 10 dt. What do I get over here? Well, hey, integral of the derivative, that's just the same thing. Okay? E negative t over 10 d of t. And by the way, I get a constant out of this. I'm going to call it C1 for a reason that'll be obvious in a second. And I take the integral over here, and I get, okay, I get negative 10,000, and I divide that by negative 1 over 10, e negative t over 10, and again I get a plus, I get another constant, CT. Okay? And alright, so that's great. This part right here turns into 100,000. Alright? So that's great. That's great. Now all I have to do is just solve for dt. Okay? Now one little note here before we go forward. I have a constant here, so some arbitrary constant. I have some arbitrary constant over here. One thing I can do is I can just put them together, right? Equals, yes, 100,000. E negative t over 10 plus c of t minus c1. And just put those two guys together. The thing is hey, arbitrary number minus an arbitrary number. That's just an arbitrary number. Okay? So in the future, you just only have to write one c. Okay? Alright, so where do I go from here? Well, hey, I can just now divide this guy out. Alright, so I get e 100,000 e negative t over 10 plus c divided by e negative 10 over t, which is then just equal to 100,000 plus c e negative t CET divided by 10. Okay. Okay. So, I now have the solution to this problem, or at least I have the form of it. I still have to nail down this C because but I at least have that. So let's try and nail down that C. So I started off with $80,000 of debt here. Okay. What happens if I given that fact right there? What happens given that fact right there? Let's see. I'll cut out this part right here. All right. So given that fact, I'll just apply it. Okay. D0 equals 80,000. And then I just plug that 0 into basically this function right here. So I get 100,000 plus CE negative 0 over 10. This equals 100,000 plus C times 1, which then we very quickly get that, oh, okay, so that means C is equal to negative, this would be 100,000. This is equal to negative 20,000. So what I end up having here is 100,000. My solution for all of this, the value of my debt at any given time will be 100,000 minus 20,000 times e to the t over 10. There's my solution. And does the solution make sense? Does the solution make sense? Well, let's look at the graph of this guy, okay? Let's look at his graph. Let's see. So when d equals 0, it's 100,000 minus 20,000, which is all the way up here at 80. And then I have this exponential function, which is getting larger and larger, but it's negative, so it's decreasing like this. Okay? It actually keeps going down in negatives, but once it gets to 0, my debt no longer exists. Okay? So that means, hey, I will eventually, one day, I pray to God, pay off this debt. Okay? It will happen eventually. Okay? Alright, and then it's very straightforward to solve for something like, well, I'm very curious about when dt equals 0, right? That all you have to do is basically set the equation to 0, do a bit of algebra 2, and then you're done. Okay, and you can find out what your t value is. Alright? Okay. So, that is fantastic. Alright? So now we know. Now we know. And let's see, one other thing though. One other thing I want to make a comment about though is, let's just change the problem. Actually, let me review this and then I'll change the problem just a little bit. So how do we do that? How do we do that? We start off with this equation right here, where, okay, how is my debt changing? At what rate is it changing? It's changing at a rate of, it has this positive part, which is 1/10 of the current value of my debt, all right? And then minus $10,000, which is the amount I can afford to take away from my income, okay? And then what happened is, okay, I first just algebraically move this over. That feels natural enough. In some way, I want to sort of combine these guys, and I'm sort of, because derivative stuff right here kind of reminds me of the product rule, but I don't have a g for this. So I think, okay, what happens if I multiply it by some function? Okay, what would happen there? I figure, oh, well, this would work if the derivative of mu, derivative of the integrating factor, equaled negative 1/10 of itself. And I know what function does that. So I plug in that function, I do the reverse product rule, I get this equation right here, I integrate to get rid of that derivative, and then it's just algebra. And then it's just algebra. I plug in a value, more algebra, and I'm done. And I'm done. And I know my debt. All right? So, one other thing I'd like to just comment here is, let's imagine, hypothetically, that instead of having $80,000 of debt, let's just say I had some problems in school and I changed the major, or I was lazy or something like that, and I had 5 years of school, 5 years instead of 4. So I had $100,000 right there. Right? I had $100,000. Well, how would that change things? Change things in the following way. I'd have 100,000 over here of debt equals D0. Plug it in over there, 100,000 plus CET0 over 10. All right, so this then turns to 100,000 equals 100,000 plus C times 1. So therefore, C equals 0. My solution is dt equals 100,000. That means that, oh, I started at 100, and I stay there. I stay there. I stay there for all of time. I will never pay off my debt. Okay? If I only am paying it off with this level of money, and I have this amount. And you guys can imagine what happens if I really messed up and I had $120,000 of debt at the end. I had stayed for 6 years. This would then look like this, and C would be positive number. So the ultimate answer would be 20,000 ET over 10. I have a constant number plus an exponentially increasing one. So I start off at 120, and it skyrockets, and then I hit 0 because I declared bankruptcy. No, I can't do that with student debt, I'm just joking. So, those equations, those final solutions make sense, okay? And we got to this by this, okay? Now, one thing I want to say is, let's see, okay? Now, let me just generalize this, all right? Let me just generalize a bit, okay? And then we'll move on, because this sort of problem happens in all kinds of different situations. Okay. If I, let's just say, was describing it in the following way, where my derivative was y of t equals a of t, y of t plus b of t, all right? So if you remember, like, this is the rate of change in my debt before, this is like current debt, this is the APR, the interest that I'm paying. So we can imagine maybe that's variable interest rate, you know, goes up and down depending on what the Federal Reserve decides. Those beautiful, intelligent people in the Federal Reserve. And then this is the amount that I'm sort of paying off, which might vary. And maybe I'm paying off less at the beginning of my career, more at the end of my career. Okay? So you can imagine it's much more variable. Okay? What would happen there? Well, I can do all the same manipulations here. Okay? A of t, y of t equals b of t. I can do that same. I can add that same integrating factor, which is going to be e integral of a of t dt, or EAT for short. I'm going to do that, EAT, y derivative of t minus, this should be negative, minus a of t e negative a, big A of t. Almost done here, guys. Y equals b of t times e a of t. This then turns into I recognize that, hey, this right here is EA of t times y of t. I just integrate this guy, integrate b of t e negative a of t dt. This guy turns in, we end up with just straight up, after a little bit more work, a little more algebra, I finally get y of t equals the integral of b of t e negative a of t plus c divided by e, this should be negative, e a of t. That's our solution. And that's the general solution. And what's great about that is, hey, if I just know a and b, I can just plug that into there directly. Okay? Now, I don't recommend doing that. I don't recommend memorizing that because then you will never remember it. What I recommend is going through this process each time, remembering the basic fundamental ideas that I use for that of, hey, let's put this over here because that'll probably look better. I want to combine these somehow. Oh yeah, reverse chain rule. How do we do that? Reverse product rule. How do we do that? Integrating factor. What integrating factor? The one that makes it so that this is the original, this is the derivative. What do we do after that? Integration algebra. Okay? I know that feels painful and involved, but you have a much better time trying to remember that process than memorizing this formula. At least you'll remember it for longer than the exam. Okay? Okay. All right, and so that's all I have to say about that. Okay.